Hey folks, how y'all doing? Um, we're finishing up chapter 4 today, so let's go ahead and get started. This is a section on diagonalization. So we're going to start with this example, which involves material we've seen before. We want to find a diagonal matrix which is similar to this matrix. So what we're going to do is first find the eigenvalues and the eigenvectors for A. So we're going to find the eigenvalues. That means we're going to subtract lambda from the diagonal. 4 minus lambda, 1, 2, 3 minus lambda. Take the determinant and set that equal to 0. That gives us 4 minus lambda times 3 minus lambda minus 2 equals to 0. When I FOIL this out, I'm going to get lambda squared. That's my last term. I'm going to do that one first. Minus 7 lambda plus 12 minus 2 equals 0. Or lambda squared minus 7 lambda plus 10. That factors into lambda minus 2, lambda minus 5. And so we have two eigenvalues, 2 and 5. And those are the eigenvalues. Then we're going to find the eigenvectors. And so we're going to solve a homogeneous system here for both lambda 2 and lambda is equal to 5. So the homogeneous system for lambda equals 2. 4 minus 2 is 2. And 3 minus 2 is 1. That's going to be easy to row reduce. And the homogeneous system for lambda equals 5. 4 minus 5 is negative 1. And 3 minus 5 is negative 2. So in this case, all we have to do is just row 2 minus row 1. And we have this. That's telling me that 2x plus y is equal to 0. So the vector that I'm thinking about might be negative 1, positive 2. 2 times negative 1 plus 2 adds up to 0. So there's one eigenvector. This one's easy to row reduce also. This is just row 2 plus 2 row 1. That gives me negative 1, 1, 0, 0, 0, 0. And negative x plus y is equal to 0. That's going to be a vector where x and y are the same, like 1, 1. All right. So what we have now is that the matrix A takes this vector v1 by 2 and v2 by 5. And so the alternate basis v1, v2 is scaled by A. What we're looking for is a diagonal matrix. And that is what matrix does this, but to the standard vectors, scales E1 by 2 and E2 by 5. And that's the matrix 2, 0, 0, 5. E1, if we scale it by 2, just goes to 2, 0. E2, if we scale it by 5, goes to 0, 5. And so This diagonal matrix geometrically does the same thing to the standard basis that the original matrix A does to our alternate basis. Um, so to write the diagonal matrix, all we really need is the eigenvalues up here, and put the eigenvalues on the diagonal, and we're ready to go. We don't need the eigenvectors to answer this question, but it's going to help us with the next example. Ready to move on? So the diagonalization of a square matrix is the relationship A equals PDP inverse that not only tells us what the diagonal matrix is, but the coordinates matrix, the change of coordinates matrix that lets us convert between standard coordinates and our alternate basis coordinates. And so how do we write that diagonalization? So we already know that the diagonal matrix D is the matrix 2, 0, 0, 5. This information comes from the eigenvalues. The change of coordinates matrix P turns out to be the eigenvectors in the same order. So -1, 2 in the first column and 1, 1 in the second column. We just have to make sure that the eigenvector for 2 is in the same column with the 2, and the eigenvector for 5 is in the same column with the 5. This information comes from the eigenvectors. And that's because if we want to convert a matrix from alternate coordinates back to standard coordinates, all we have to do is work out a linear combination. We multiply the first coordinate by the first column, and multiply the second coordinate by the second column. P inverse, we have to find the inverse of this matrix, but that's just working out an inverse. That's 1 over the determinant is going to be -1 minus 2 is -3. And then we switch the entries in the main diagonal, so that becomes 1 and this becomes -1. And we switch the signs along the other diagonal, so this becomes -1 and -2. When we multiply by 1 over -3, we get -1/3, +1/3, 2/3, and 1/3. And so we're ready to finish the diagonalization. The original matrix A is equal to -1/3, 1/3, 2/3. Sorry, P comes first, not P inverse. P and then D inverse. So 1, -1, 1, 2, 1 times 2, 0, 0, 5 times P inverse, -1/3, 1/3, 2/3, 1/3. And we call this the diagonalization of A. It includes the diagonal matrix from the previous example, plus the converting matrices that convert us back and forth between the two systems. All right, let's move on. So here's a 3 by 3 example. This is going to be a little harder. We want to determine the diagonalization for this matrix here. And there you go. So again, first thing we're going to do is find the eigenvalues. All right. So we're going to take the determinant of the matrix 2 minus lambda 0, 0, 1, 2 minus lambda -1, 1, 3, -2 minus lambda. Set that equal to 0. I'm going to do a cofactor expansion along the top row. And that's going to give me 2 minus lambda times the cofactor in the 1, 1 position. And the cofactor in the 1, 1 position is the determinant of the smaller matrix 2 minus lambda negative 1, 3 negative 2 minus lambda. And that's equal to 0. So this is 2 minus lambda times 2 minus lambda negative 2 minus lambda plus 3. And this becomes lambda squared. The inner term and the outer term cancel. This is going to be minus 4 plus 3. That's a 2. Well, minus 4 plus 3, this is just lambda squared minus 1. And that factors into lambda plus 1, lambda minus 1. And so my eigenvalues are 2, negative 1, and positive 1. All right. Now we're going to find the eigenvectors. So the homogeneous systems we want to cover when lambda is equal to 2, this is 0, 0, 0, 1, 0, negative 1, and 1, 3, negative 2 minus 2 is negative 4. Augment that with all zeros. When lambda is equal to 1, 2 minus 1 is 1, 2 minus 1 is 1 again, and negative 2 minus 1 is negative 3. And augment that with zeros. And when lambda is equal to negative 1, we get 2 minus negative 1 is 3. And negative 2 minus negative 1 is negative 1. Augment that with zeros. All right, we're going to have to solve this. All of these, actually. So to put this in echelon form, the zeros go at the bottom. And let's see, let's do some work here. So I'm just rearranging rows right now. And then we're going to take row 2 minus row 1. And we're going to get 1, 0, negative 1, 0, 0, 3, negative 4 minus 1 is negative 3, 0, 0, 0, 0, 0. And so z is free. And we're told that x minus z is 0. And if I divide by 3, I get also y minus z is equal to 0. So z could be any non-zero number, and x and z are the same. And so our first eigenvector is 1, 1, 1. All right. So then let's look at our next eigenvector. Let's see. If we take row 2 minus row 1 and row 3 minus row 1, then we get 1, 0, 0, 0, 0, 1, negative 1, 0, 0, 3, negative 3, 0. And then we can take row 3 minus 3, row 2. And that gives me 1, 0, 0, 0, 0, 1, negative 1, 0, 0, 0, 0, 0. And so x is 0 and y minus z is 0. So z can't be 0, but y and z are the same. And so our second eigenvector is 0, 1, 1. X has to be 0, though. All right, let's look at our last one. Take the top row and divide it by 3. So that gives us 1, 0, 0, 0. 1, 3, negative 1, 0. And I'm going to go ahead and take row 3 minus row 2 and make this all zeros. And then take row 2 minus row 1, and we'll get 1, 0, 0, 0, 0, 3, negative 1, 0, 0, 0, 0, 0. And so x is equal to 0, but this time 3y minus z is equal to 0. And so if y is 1, z would be 3. And so that's our third eigenvector. We almost have the information we need for the diagonalization now. So the diagonalization is that A is equal to P comes directly from the eigenvectors. So 1, 1, 1 in the first column, 0, 1, 1 in the second column, 0, 1, 3 in the third column. D comes directly from the eigenvalues, 2, 1, 0, 0, 0, 1, 0, 0, 0, negative 1. What we're missing is the inverse of this matrix. This is P. We now need P inverse, and I don't have a lot of room to find the inverse, but let's work on this. So the way we're going to find the inverse, and I'm going to squeeze that in to this little area here. I'm sorry for squeezing this in. So we're going to take A, augment it with an identity matrix, and then put this into reduced echelon form. So I'm going to take row 2 minus row 1 and row 3 minus row 1. And that gives me 1 minus 1 is 0. 0 minus 1 is negative 1. And again, 1 minus 1 is 0. 0 minus 1 is negative 1. And then we'll take row 3 minus row 2. And that's going to give me 1, 0, 0, 1, 0, 0, 0, 1, 1, negative 1, 1, 0, 0, 0, 2, negative 1 minus negative 1 is 0, negative 1, and 1. All right. Now we're going to have to put this into reduced echelon form. So I'm going to divide this row by 2. Row 3 divided by 2. That's going to get me 1, 0, 0, 1, 0, 0, 0, 1, 1, negative 1, 1, 0, 0, 0, 1, 0, negative 1 half, positive 1 half. And then finally, we have to get rid of this 1 up here, so row 2 minus row 3. That's going to give us 1, 0, 0, 1, 0, 0, 0, 1, 0. Negative 1 minus 0 is still negative 1. 1 minus negative a half is 3 halves. 0 minus a half is negative 1 half. And then finally 0, 0, 1, 0, negative 1 half, positive 1 half. So we have the numbers that will go here. Negative 1, 3 halves, negative 1 half, 0, negative 1 half, positive 1 half. And that's the inverse of this matrix here, and we have completed the diagonalization. All right, let's move on. So we'll look at this matrix A, And we want to compute a to the 500th power. I say the result may surprise you. I hope it does. Um, I've already given you the eigenvalues and the eigenvectors so that we don't have to spend time, and more importantly, we don't have to use screen space to do those calculations. So what we now know is that the diagonalization of A is P times D times P inverse. P comes from the eigenvectors 2, 3, 1, 2. D comes from the eigenvalues 1, 0, 0, -1. And now P inverse, we'll have to do that work. So we want to find the inverse of 2, 3, 1, 2. Reading down. So that's 1 over the determinant. The determinant is 4 minus 3. That works out nicely. That's just 1 over 1. The 2's switch places. Can't tell anything happened, but the 2 switch places. And the 1 and the 3 switch signs. And so the determinant of this matrix is 2, -1, -3, 2. Now, using this diagonalization, a to the 500 power is just P times D times P inverse times P times D times P inverse times P times D times P inverse times P times D times P inverse 500 times. But one of the things that we know is that any time that P inverse and P are next to each other, they cancel. The P and the P inverse on the outside don't cancel because they're not next to each other. And so this is just the same thing as P times D, 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 D 500 times. In other words, this is just P times D to the 500th power times P inverse. All right. Well, then P times D to the 500th power times P inverse is 2132 times the matrix 1, 0, 0, -1 to the 500 power times 2, -1, -3, 2. But this matrix here, when we raise it to the 500 power, we can solve this problem without having to multiply this out. Because a diagonal matrix only represents scaling. E1 just scales by a factor of 1. And if you scale by 1, there is no change. And it doesn't matter whether you do this 1 time or 500 times. If there's no change at any stage, then E1 is going to stay exactly the same. This is going to be just 1 times 1 times 1 times 1, 500 times. And that's still just 1 times 1, 0. And E2, it does change, but changes by -1, which means E2 flips from positive to negative when we multiply it by 1 time. But if we multiply it an even number of times, then the first time will cause it to flip to negative. The second time causes it to flip back to positive because we're multiplying by -1, and then we're multiplying by -1 again. And since 500 is an even number, then -1 to the 500 power is just +1. So I've scaled this matrix by 500. E1 never changes. E2 flips back and forth, but since it flips back and forth an even number of times, this becomes 1. Well, this is the identity matrix. And the identity matrix times anything is just itself. So I'm going to go ahead and combine these. And this just gives me 2, 1, 3, 2 times 2, -1, -3, 2. But this is just P times P inverse, and any matrix times its own inverse is the identity matrix. So surprisingly, this matrix here, raised to the 500 power, gives me the identity matrix. That is the surprising answer, that this is a 500th root of the identity matrix. All right. So diagonalization gives us a fast way of calculating a power of a matrix. We can use this trick here to cancel all but one of the p's and p inverses. The ones on the outside don't cancel. Everything in the middle does cancel. A diagonal matrix to the 500 power is just scaling each column to the 500 times. And 1 and -1 scale very easily, but if this was a 2, we would have to calculate the gigantic number 2 to the 500, and that would be right here in this calculation. Then we'd actually have to multiply this out, and we'd get a very large answer. But we know how to calculate that. All right, let's move on. When is a matrix not diagonalizable? So this is a matrix that's not diagonalizable. And we're going to try to find out why not. So we're going to first find the eigenvalues. In this case, the eigenvalues are really easy to find. Because we want the determinant of 2 minus lambda 1, 0, 2 minus lambda. But this matrix is in echelon form, so the determinant is just multiplied down to diagonal. The other diagonal is going to give me 0. And so we get 2 minus lambda times 2 minus lambda is equal to 0. And so we only get one eigenvalue. That the eigenvalue of 2 is repeated. And so the fancy way of saying this, the mathematical way of saying this, is that that lambda equals 2 is an eigenvalue with and here's the term, the algebraic multiplicity of 2. It's a repeated root. It's a root that shows up twice. And that means when we go to find the eigenvectors, we only have one homogeneous equation to solve. 2 minus 2 is 0. 2 minus 2 is 0. And this is somewhat unusual. The free column is over here. We have a leading entry in this column. So this row says that y is equal to 0 and x can be anything. And so we have an eigenvector, x could be anything, but we only have one eigenvector because there's only one free variable. And so we do not have enough eigenvectors to form a basis. Now you might think, well, we could pick another value for t. like 7, and then we could have 1, 0, and 7, 0. But those are not linearly independent. And so they still can't form a basis. And so we don't have eigenvectors to form a basis. And because we can't form a basis, we can't calculate a square matrix P that is invertible. We only have enough for one column. We don't have enough for the second column. Now the notation here, the terminology here, is that lambda 2 has only one eigenvector. And the way that we say that is algebra lambda equals 2 is an eigenvalue with a geometric multiplicity of 1. So the number of eigenvectors that we get is called the geometric multiplicity. Let me not scribble through that, try to underline it instead. There we go. And these have to match in order to be diagonalizable. If this is a repeated root, then we would have to have 2 eigenvectors to make that happen. Sometimes that happens, um, but it didn't happen here. So lambda is 2 is an eigenvalue that has a geometric multiplicity of 1 because there's only one eigenvector that scales by a factor of 2. Um, so anyway, that's the terminology. If these are different, A is not diagonalizable. Let's try one more example and we will wrap up. So let's look at the eigenvalues and the eigenvectors for this matrix here. All right. So we would like to find the eigenvalues first. So we take the determinant along with by subtracting lambda from the diagonal. So this is 1 minus lambda, 1 minus lambda, 2 minus lambda. Set that equal to 0. This matrix is already in echelon form. So 1 minus lambda times 1 minus lambda times 2 minus lambda is equal to 0. And so we get 2 eigenvalues. Lambda is equal to 1 with an algebraic multiplicity of 2. Because it's a root 2 places, and lambda is equal to 2. And we don't have to say with algebraic multiplicity 1. If we don't say, that's just automatically applied. All right. So now we have to find the eigenvectors. And so we have two systems of equations to solve. So when lambda is equal to 1, we get 0, 1, 0, 0, 0, 1, 0, 0, 1. And when lambda is equal to 2, we get negative 1, 1, 0, 0, negative 1, 1, and 0, 0, 0. All right. I'm going to get rid of this by just taking row 3 minus row 2. And we'll get 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 0. I have a leading entry in columns 2 and 3, but column 1 is free. The top equation says that y is equal to 0, z is equal to 0, but x is free, and so x could be anything. But since I only have one free variable, I only have one eigenvector. And so lambda is equal to 1 has algebraic multiplicity 2, but a geometric multiplicity of 1. Um, all right. As they don't have the same multiplicities, then we cannot diagonalize this matrix. But let's go ahead and find the eigenvectors for this matrix. Um, let's see. We have a leading entry in columns 1 and 2, and so this time z is free. So negative x plus y is 0, and negative y plus z is 0, and z is anything. Well, this tells me that y and z are the same, and this tells me that x and y are the same. So all three of these are the same, and so that's an eigenvector for lambda equals 2. So we have a 3 by 3 matrix, but we only have two linearly independent eigenvectors. That's not enough to form a basis for my alternate coordinate system, and therefore we cannot diagonalize this matrix. All right. So I hope this helped. We're going to start chapter 6 in the next video. Take care. Bye-bye.